Hello and welcome to the first topic of this course, topic 1.1, scalars and vectors. This is a very foundational topic and a very foundational unit in general, but especially this topic, you will be using this a lot in physics. You're going to have lots of opportunities to get very comfy with this, but luckily it's not particularly difficult, so should be alright that you're using it a lot, but let's get into it. So when we measure a quantity in this course, it could either be measured as a scalar quantity or as a vector quantity. And it's important to distinguish which one it is when you're measuring something. So let's start with a scalar quantity. If you were to come up to me and ask, how hot is it outside? And I tell you, it's 80 degrees. That is all you need to know. I have given you all of the information to answer your question. And what I've given you is just how much of that quantity of temperature there is. All I've given you is what we call a magnitude. And there's some other examples of scalar quantities would be, like I said, temperature, time. If you ask how long has it been, all I need to tell you is the amount of time, how much time, nothing else, and mass. If you ask how much mass does something have, and I tell you, oh, it's got 20 kilograms, that's it. That's the whole description. Now, if instead of how hot it was outside, you would have asked me, how do we get to the nearest bathroom? And I tell you, you're going to want to go about 200 feet. Notice I pause there because you're probably expecting something more. You're going to look at me like I'm stupid because that does not answer your question at all. You don't know where 200 feet is going to take you. You're asking where's the nearest bathroom. You can go 200 feet anywhere. If I said instead of that 200 feet and pointed and said 200 feet that way, if I said 200 feet down that hallway, 200 feet to the right, then I've answered your question. Because instead of just a magnitude, I've given you both a magnitude, the 200 feet, and a direction. And that is very important. That's what a vector quantity is. Some examples of vector quantities are displacement, which is what you're asking for in the bathroom example. You're effectively asking, how do I have to displace myself to get to this bathroom? Velocity and acceleration. Now, if you don't know what any of these quantities are, don't worry, I'm going to explain them in the next video. But for now, just know that these all rely on direction. What you can see, I'll go over it quickly here if you just want to see why they rely on direction. For example, acceleration, it's if you're in a car, both your accelerator and your brake are going to apply an acceleration to your car. But it's very important what direction, because if you just say, if you're driving and your driving instructor tells you apply an acceleration, you're going to want to know what direction to apply the acceleration because that's going to change whether you press on the brake or press on the accelerator. And notice here, in all of these quantities, I have put arrows over them. That is how we denote that something is a vector. The arrow shows that it relies on a direction. Now I'd like to say, just before we go into the next part, I know that this topic only says scalars and vectors in one dimension. However, I'm just going to go over them in 2 dimensions, include that in there because it's really not that much harder to do it in 2 dimensions, and I'm really leaving out a whole lot if I just do it in 1 dimension in this video. So now we're going to talk about how we can represent these vectors. Scalars, we don't really need to talk about how to represent them because it's just magnitude, not very much other than that. So the first thing we do when we start representing vectors is we define our directions. So if we're using a coordinate plane here, that can easily tell us what exactly each direction is. And these can represent up, down, left, right. This can be north, south, east, west. But what it will most commonly be represented as, no matter what the physical interpretation is x, y, and negative x. These are our 4 directions. And a vector can have a magnitude along any of these directions. So if I have an arrow, I say this is 3 miles, then it has a magnitude of 3 in the positive x direction, as we can see, and a magnitude of 0 in the positive y in any y direction. So we'd say it has a magnitude of plus 3, 0 miles. And usually we can leave out the plus because it's implied that that's there, but just to show you that that's in the positive x direction, I'm going to include that. And then we can also do, if we have 3 miles up here, that's 0 in the x direction, positive 3 in the y direction, miles. Now, if we were to have a vector that looks something like this, and we were to say this is 5 miles at 37 degrees. So before, we could either represent this as the components here, the magnitudes of the components, because we know the direction, or we could just say the overall magnitude of the vector in the overall direction. So this is 3 miles in the positive x direction over here on the left, and then this one going up is 3 miles in the positive y direction. And there's usually not much of a difference. Well, not usually, but in these two cases, there wasn't much of a difference. But when we get to vectors like this, there is going to be a difference. We can either represent this with the overall magnitude and direction, which we could say 5 miles at 37 degrees above horizontal, or we can break this into its components. And we're going to do that with trig. If this is 37 degrees, we know that sine of 37, we're just going to say, generalize it and say sine of theta is opposite over hypotenuse. So if we're looking for this opposite side, we just multiply both sides by hypotenuse. We get hypotenuse sine theta is this opposite side. So in this case, it's going to be 5 sine 37, which is just 3. And then similarly, since we knew that cosine theta is adjacent over hypotenuse, then the adjacent side is hypotenuse cosine theta, which in this case is going to be 4 miles. So we can also represent this vector as plus 4 plus 3 miles. Two ways to represent it. Going back and forth between these two ways is going to be pretty important. Now, let's see what happens if we're going to add vectors together. So when we're adding vectors together, what we want to do is just turn all these vectors into the components and add up the components in both directions. So starting with this one, we have this is 0, 10 meters. Up here, we have negative 4, 0 meters. And then this one here, we're going to have to break into its components. So I'm just going to show that down here. I apologize, these drawings are not to scale. 30 degrees. So using what we talked about earlier, if we're going from 20 meters and we want to break it at 30 degrees above horizontal, want to break it into two components, we're going to have the y component is 20 times sine 30, which is going to be 10 meters. And the x component is 20 times cosine 30 degrees, which is going to be 17 meters. So now we can see that this vector has components 17, comma 10 meters. Now, we just add all of them up. 0, 10 meters, 17, 10 meters, and negative 4, 0 meters. We get 17 minus 4 is 13, 10 plus 0 is 20, and that is our final, we call this the resultant vector. Now, this resultant vector would be if we started from here, started from there, and just drew all the way up here. Now I'm just going to erase some things and show you we worked to get the components of a vector from its overall magnitude and overall direction. But here, now that we have the components, let's see what we can do to find the overall magnitude and overall direction. Another thing that's going to be important in this course to be able to do. So I'm just going to erase some of this here. And I'll rewrite this as just the original, not the resultant vector here. So again, not to scale, I'm sorry. So we have this, and we know it's 13 meters here and 20 meters here. We want this side, we're going to call it C. We want this angle. Now, if you recall from your geometry classes, getting C is just going to be through use of the Pythagorean theorem. And when we do that, just take the square root of the sum of the square of both of the sides. We're going to get that it's about 24 meters. Now, what about for this angle? Luckily, with trig, every trig function can be represented as the quotient of two sides. So if we have an angle, we're looking for this angle, and we have any two sides of the triangle, we can find that angle. We just need to know what trig function we have to use. So if we look from this angle, we have the opposite side and the adjacent side. And the function that deals with opposite over adjacent is going to be tan. So we have tangent of theta is 20 meters over 13 meters, meaning theta is going to be the inverse tangent of 20 over 13. Now, you might not always have tangent, and technically, since we found out this other side, we could do it with any trig function, but you want to make sure you're using the sides that you know, and because this is a rounded quantity, this 24 meters, and also it just makes it easier. You don't have to work backwards. You can find this angle without having to find anything else first. And then also it makes the angle more accurate. So this right here, we're just going to get 57 degrees. So we found that this is 24 meters at 57 degrees above horizontal. You could also say, another way to say that would be it's 33 degrees, 24 meters at 33 degrees below vertical. Horizontal and vertical in this case are ways to say the positive x and the positive y direction. Now, we could also, if we had, let's say, north, south, east, west as the directions, we could say this is 57 degrees north of east. We could say this is 57 degrees up of right. There's a couple different ways we could say that, but either way, it's 24 meters at an angle of 57 degrees. That's going to be all for this video. Let me know if you have any questions, and hopefully you'll join me for the next video where we'll be discussing position, velocity, and acceleration that I mentioned earlier.